Before we start Chapter 7, I want you to imagine for a second that you could not see and that you have never seen. Alright? Now, someone is going to try and describe color to you, and what color is, and what color looks like, and how color influences the entire world around them. And you've never seen it. You have no experience whatsoever of what color even means as a concept. The issue we're about to address is that things on the scale of electrons, of subatomic particles, exist in a world where the properties and behavior of objects work in a way that we have no experience with whatsoever. They do things and they act in ways that make absolutely no sense at all on the macroscopic scale, but it's understanding these properties and understanding how, even though it makes no sense on the surface, that these things behave, help us to understand electrons, and through electrons, the properties of everything chemical around us. So just keep that in mind as we go through this, that we are going to be talking about some stuff that may not make sense, but keep an open mind and give it a shot. Why are we bothering to get into this whole quantum physics, Einstein, Schrodinger, high-level scientific kind of physicsy kind of stuff? We're chemists, right? But the ideas here are central to trying to figure out how in the world electrons behave. And how electrons behave is critical to understanding physical and chemical properties of substances. Well, if you think about it, why is it critical? Well, just think about what electrons do. Electrons are what hold elements to each other, atoms of different elements, one to the next, and gives them the shape which gives them their physical properties, chemical versus ionic bonding, for instance. And electrons and what is stable or unstable also is what gives the property of whether or not those bonds change partners, whether or not a new compound is more stable in forms instead of the old compounds. And this is exactly what gives something its chemical reactivity and its chemical properties. So the electrons are central, really, to understanding chemistry. So we have to understand the electrons themselves. Now think about electrons. Think about their size. This is a little artistic representation of an electron, but it's not really this particle floating around through space, at least not to the best of how we can understand it. But size-wise, mass-wise, we're looking at an unbelievably tiny thing. Less than a trillionth of 1 gram. And how big is a gram? Well, a dime weighs about 10 grams. So a tenth of that, and then a trillionth of that, and that's an electron. That's almost impossible to picture. Well, picture this as well. A single speck of dust has more electrons on it than the whole number of people who have ever existed at all on Earth. So as unimaginable it is to picture that number of people, is just as unimaginable to try and picture how many actual electrons are crammed into one tiny speck of dust that's barely big enough for us to see as it is. So they're small. They're beyond small. They're kind of the epitome of small and still have it be somewhat of an object. So to talk about this kind of world, the quantum world, which you can just say the very, 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 very to the 23rd power small world. Okay? So when things get small enough in this quantum world, like we're talking electron size things here, the way things work change. One of the things they talk about right here in section 7.1 is one of the bizarre properties that things can have at this level of scale. Like the idea that if you have not observed an object, that it can simultaneously exist in multiple states. Okay, what does that mean exactly, right? Well, imagine we have a nucleus, and through a certain type of radioactive decay, we can have a particle, like an electron-sized particle, ejected from that nucleus. Well, with the size of electrons, we can actually have a system where if we have not observed this particular particle, this is the same particle, just representing it twice, that particle that has come off the nucleus and at the very same time could exist here as still on the nucleus. So until we observe whether or not that electron has moved off or not, it's not just that we don't know which it is, it actually has the properties of both, which makes no sense, and yet that's how it works. The Schrodinger's cat example was put forth in a paper basically way back in 1935, a scientific paper trying to explain this quantum nature of the world. And Schroeder put up a thought experiment of how we could take a cat, and he did not like cats, as you're about to understand, put them inside of a steel box that you can't see the inside of, set up a little radioactive sample that's going to emit these particles that we just talked about, and a device to measure whether or not the particle has been emitted. So inside that box is that whole system that can exist at the same time as a particle is emitted and a particle is not emitted. But we're hooking this up to a macroscopic object to where if it detects that that particle was emitted, it'll release a little hammer, and the hammer knocks over a flask of poisonous gas. Dead cat. If the particle is not emitted, cat is still alive, flask is unbroken, cat is perfectly fine. So the quantum mechanical understanding of the universe says that since this particle exists both as emitted and not emitted until we observe it, and by the act of observing it, force it into one state or the other, either emitted or not having been emitted, that this whole system is kind of in limbo and existing at both states at once, meaning the cat is dead and the cat is alive, and both are happening simultaneously in that box until we open it up and look inside and see what's there. Alright, so how does this make sense? Well, the short answer is, it doesn't. Right? Just like color being described to someone who has never ever in their life been able to see color doesn't really make sense. You can only kind of give some descriptions and kind of try to describe things in kind of abstract terms, but a concrete, exact understanding of what that is just isn't obtainable unless you can see it, unless you can experience it in some way. And you cannot experience the way the quantum universe works on a macroscopic scale. It just doesn't make sense on that scale because nothing actually works that way on the scale of a cat. And so that experiment isn't real. You can't actually have a cat that is both alive and dead or some sort of weird zombie intermediate. It just doesn't happen that way, but that's how it does happen on the electron size scale.